Hi everyone, I am Sunima Ratnayaka from the National University of Singapore. I am presenting my talk on our paper titled Characterizing the Cost Accuracy Performance of Cloud Applications. Here is the outline of my talk. I will start off with the motivation for our work, presenting the research questions and contributions. Then I will explain our approach, followed by the evaluation, where I will discuss the key insights. Cloud computing has been around for many years now, gaining immense popularity due to its attractive service models. Clouds offer hundreds of resource types with different cost and performance to cater to a wide range of application domains. Cloud resources are scalable, and the cloud consumer is charged only for the time the resources are being used, which is also called on-demand pay-per-use charging. Optimizing the resource allocation on cloud is a widely explored and a well-known research topic for minimizing the cost and time on cloud. When we talk about cloud applications, among the multitude of cloud applications ranging from simple web applications to complex scientific applications, there are some applications that produce results with a notion of accuracy. Some applications produce probabilistic outputs. In such applications, the accuracy of the output relates to the application's resource demand. In other words, the resource demand can be changed by varying the application accuracy. On scalable cloud resources, such applications open up a new opportunity for the cloud consumer to trade off the application accuracy in return for cost and time savings on cloud. In the context of scaling application accuracy on cloud, we address two main research questions. First, given an application with a cost budget and a time deadline, what is the highest achievable accuracy on cloud? Secondly, what is the trade-off between cost, time, and accuracy on the cloud? We intend to find answers for these two questions in this work. Investigating the accuracy performance of cloud applications, this paper makes the following contributions. We present a measurement-driven modeling approach for investigating the relationship between the time, cost, and accuracy on cloud. We expose sweet spot application configurations where cost and time can be reduced with insignificant loss in accuracy. We show the existence of cost accuracy and time accuracy Pareto optimal frontier with opportunity to reduce cost and time by selecting Pareto optimal configurations. Finally, we propose metrics for characterizing accuracy performance of cloud applications that can be used for efficient resource determination. As the representative application for accuracy scalable applications, we selected convolution neural networks. Convolution neural networks, also known as CNNs, produce results with a notion of accuracy or a probability. In this paper, we use two CNN example applications that perform image classification. We selected CafeNet, a CNN with 5 convolution layers, and GoogleNet, which contains 54 convolution layers. Since training CNN is largely a one-off task, we focus on the inference performance of CNNs and use the datasets from ImageNet project in our experiments. To vary the accuracy and resource demand, we use pruning as a technique. Since convolution layers consume the major portion of CNN inference time, we only focus on pruning convolution layers. We use top 1 and top 5 accuracy metrics to evaluate the correctness of the inference result. The experiments were conducted in multiple resource types from Amazon EC2 Cloud having NVIDIA K80 GPUs. Our approach takes in the application, the cloud resources, and user constraints such as the time deadline, cost budget, and the number of inference images, and outputs a list of inference accuracy configurations with predicted cost, time, and the resource configuration to execute it on. The TAR and CAR metrics used for characterizing the accuracy performance are also computed. We will discuss CAR and TAR in detail later in this talk. This is a summary of our models that we use for determining the execution cost and time on cloud resources for a given CNN degree of pruning. Moving on to the evaluation. In this talk, we discuss the key insights with results from CafeNet CNN. To understand the effect of accuracy on execution time, we prune the CNN one layer at a time and observe the change in time and inference accuracy. We observe that there are many sweet spots where the inference time could be reduced with no change in accuracy. For CafeNet, we can achieve up to 1/4 reduction in execution time by leveraging these sweet spots. Moreover, we observe that the inference time is not directly proportional to the number of operations in the convolution layer, thus it is non-trivial to pick the best layer to prune. To understand the dependency between CNN layers, we combine multiple sweet spots identified in single-layer pruning experiments and observed the behavior of time and accuracy. The shown plot illustrates the accuracy and inference time for non-pruned combination of sweet spot in convolution layer 1 and 2 and the combination of sweet spots for all convolution layers in CafeNet. We observe lower execution time but also loss in accuracy. However, with proper understanding of the dependency between layers, we can yield the advantage of combining sweet spots. For example, compared to the non-pruned version, combining sweet spot in convolution layer 1 and 2 results in 1/3 reduction in time with just 15% reduction in top 5 accuracy. The experiments and results discussed so far assume no change in the resource configuration and only focused on the time accuracy trade-off with changing applications' degree of pruning. To leverage the scalable cloud resources to further optimize the time accuracy performance, we investigate the relationship between time and accuracy in the presence of the large resource configuration space. This plot shows the feasible configuration space for executing CafeNet within a time deadline of 10 hours. As cloud resources, one resource instance each from P2X large, P2 8X large, and P2 16X large resource types have been selected. We observe a large number of feasible configurations and 5 Pareto optimal configurations. The Pareto configurations span a time range of 3 to 5 hours with accuracy spanning 27% to 53% and 45% to 78% for top 1 and top 5 accuracy respectively. Selecting a Pareto optimal configuration over others significantly reduces the execution time. In the shown example, up to 50% time can be saved for the same inference accuracy by selecting Pareto optimal configurations. To understand the cost accuracy trade-off in the presence of large resource configuration space, we investigate the feasible configuration space for executing Caffeinate within a cost budget of $300. Similar to the previous experiment on the time accuracy trade-off, we observe a large number of feasible configurations with 5 Pareto optimal configurations. In this case, the Pareto frontier overlaps with the time accuracy Pareto frontier that we saw in the previous slide due to the cost being the restricting factor when allocating resources in both cases. By selecting Pareto optimal configurations over others, we can reduce up to 55% in execution cost for the same inference accuracy. Like I briefly mentioned in the approach, we propose the usage of two metrics to characterize the accuracy performance of cloud applications. Firstly, to quantify the impact of accuracy on time, we use time accuracy ratio or TAR, which is the ratio between the execution time required to achieve a given accuracy and the value of the accuracy. The plot shows the spread of TAR values for a set of degrees of pruning for Caffeinate, and we observe multiple prune configurations with the same accuracy but with different inference time. So TAR represents the relative change between time and accuracy and can be used to differentiate between prune configurations, especially when we have to pick the better one out of multiple prune configurations, resulting in the same accuracy. Secondly, we use cost accuracy ratio or CAR to quantify the cost accuracy performance of a cloud application. The plots shown shows the CAR values for executing Caffeinate CNN on 6 different resource types. Plot A shows CAR when only one GPU per resource is utilized, whereas the plot B shows CAR values when all GPUs are utilized. We observe a gap in CAR across resource categories and close or similar CAR within one resource category for the case where only one GPU is utilized. When utilizing all GPUs, the CAR value scales linearly according to the number of GPUs used. CAR can be used to pick the best resource type for a given application in terms of cost accuracy performance. Furthermore, CAR combined with TAR can be used as a heuristic for efficient cloud resource allocation. We have arrived at the conclusion of my talk. In this paper, we presented a measurement-driven approach for investigating the cost accuracy and time accuracy trade-offs on cloud. We showed that multiple sweet spots exist to reduce the cost and time with negligible loss in accuracy, and that there are multiple application configurations with same accuracy for different cost and execution time. We exposed the cost accuracy and time accuracy Pareto optimal configurations that can be used to reduce cost and time on cloud. Finally, we quantify accuracy performance of cloud applications with time accuracy ratio and cost accuracy ratio metrics and propose their usage as heuristics for efficient cloud resource selection. That is the end of my talk. Please feel free to reach me if you have any questions or clarifications regarding our paper. Thank you.